My name is Orhan Eroglu, and I have been working at National Center for Atmospheric Research, or as we call it, NCAR, as a software engineer. And I'm leading the Geoscience Community Analysis Toolkit, or GeoCAT. So today I would like to talk about several software engineering efforts of GeoCAT and dig into those details. So before we get started with the GeoCAT insights, I would like to give some background information about how the GeoCAT team was first formed. It is going back to the year 2019 to the Pivot to Python initiative of NCAR. And before then, there was the NCL, which is NCAR command language for data analysis and visualization purposes of the global geoscience community, and it has served several tens of thousands of people for decades. But it was in Fortran, and it was some. There was no much scalability space for NCL, so there was a significant driving motivation for this Pivot to Python initiative, which was to develop tools in scalability in the scientific Python ecosystem. So the GeoCAT team was formed as part of this initiative, and the Pivot to Python initiative itself has an initial two-year roadmap, which was replicating the NCL's functionalities in not only computational field, but also in the visualization perspectives. And also to train and support mostly the NCL users, but in general, the geoscientists who would like to transition into Python in an easier way and move tools into an open development model where community involvement is significant. That said, we, as the GeoCAT team, focused on very similar objectives to develop scalable data analysis and visualization tools on not only structured but also unstructured or irregular meshes, and we will talk about them later in detail. And that scalability purpose, at least, drove us to be in compatibility with the Pangeo stack, which I will also detail in the coming slides. And to prioritize the community input and feedback for our project lifecycle, and getting all of our software stack not only open source but also free, accessible, and getting the community input for prioritizing our function development. Maybe a little bit more word on the open development, just to define that maybe a little bit in more detail. So first thing first, all of our software tools are open source, as many of the Python projects nowadays, and we are using them with the Apache 2.0 license. Other than that, we are providing DOIs for every single version to make our software stack reproducible by the scientists. And in addition to all of these like regular open source like project activities, we also prioritize the community input on our project management. So our project boards and roadmaps are publicly open and accessible, and the community members are available and encouraged to participate in our PM activities, as well as discussions and function development prioritization, as I mentioned before. And all of our communication and project management stuff are being handled on GitHub publicly. At this point, maybe we can start with an overview of the whole GeoCAT software stack, then we can look into each of them in detail. GeoCAT has been developing and maintaining several software projects. Almost all of them, other than NCL, the NCAR command language, are in active development right now, but the NCL is in the maintenance mode, which means we only support or provide support for Conda installation related major issues. But other than that, NCL is still accessible by the interested parties to be used. But we are not encouraging more development or more use on NCL because we are kind of in the middle of replicating all of those functions in our Python modern software stack. So let me start with the GeoCAT computational component, which is GeoCAT comp. You can also see, by the way, this is not an UML diagram. It is just for helping the audience understand what kind of relations are in between our software stack. And it is not an UML diagram, and it is having its own simple legend, as you can see in the bottom left of the diagram. But I think it is still helpful to understand the overall picture of the GeoCAT software stack. So on the right-hand side, the GeoCAT computational stack is shown, and GeoCAT comp is the actual user API with pure Python language. But under the hood, we are transparently importing GeoCAT F2Py, which is kind of a wrap-up of Fortran routines in Python. So it is still needed, at least for now, because many scientists from NCAR or outside NCAR have still some compiled language implemented codes or workflows, and they want to transfer them quickly to the GeoCAT stack. So it is still there to wrap up those type of work, but our primary computational component is GeoCAT comp, so it is highly encouraged to use directly GeoCAT comp instead of playing with GeoCAT F2Py, even though it is still a standalone software tool. On the left-hand side of the diagram, we can see the visualization tools, which are GeoCAT examples and GeoCAT Viz. GeoCAT Viz is kind of an interface to introduce higher level implementations on top of built-in Matplotlib and Cartopy projection packages. In addition, it also introduces some convenience functions to make NCL-like publication-ready plottings, as we will have a look soon. GeoCAT examples is housing plotting scripts, which I will also detail in the coming slides. Other than those, there is the GeoCAT data files. It is nothing more than a GitHub repository that houses several hundreds of dataset files, small dataset files for local data analysis or visualization purposes. But at the same time, we can still consider it as a lightweight software tool because it provides an interface with the help of the push package to access files through HTTPS or local storage. On the bottom right of the diagram, we can see the WRF Python, which is our weather research and forecast tool, which I will also talk about. And the other one is Project Raijin, our kind of brand new research and development project. Again, I will look into all of these details of all of these tools. I think we covered all of these. Maybe before going into the individual details, we can talk about the core technologies that we are relying upon for developing our GeoCAT tools. On GitHub is obvious for version control. In addition to version control, we are also putting all of our CI/CD, continuous integration and continuous delivery activities, as well as project management activities and collaboration in GitHub, again publicly. We are heavily relying on the cornerstone Pangeo packages such as Xarray for data input output and being compatible with the Pangeo stack, and Dask for scalability purposes. We are making use of Jupyter notebooks, as many folks in the Python ecosystem, for documentation and exemplification purposes. There is the Numba for just-in-time compilation for mostly our computational stuff. And in the very bottom, you can see both Matplotlib and data shader stack for visualization. I will detail the data shader stack usage of GeoCAT in the upcoming slides, but just to know for now, we are making use of Matplotlib for general plotting purposes like static plots, but for data shader, we are especially using it for high performance interactive visualization of big data data sets. I think we can now have a look at the individual GeoCAT tools. Let's first start with the computational component, GeoCAT Comp. Again, GeoCAT F2Py is just residing under the hood, but I think it is better to focus on the GeoCAT Comp. So GeoCAT Comp houses the computational or analysis operators like NCL did in the past. So currently we have implemented several functionalities ranging from climatologies and meteorology to regridding to interpolation, and some specific analysis like spherical harmonics or Fourier filter analysis as well. On the left-hand side, in the bottom part, you can see some metrics. They are increasing day by day. So we are still in the babyhood steps of making these tools to reach to more user base. Again, the computational component is heavily relying on the PanGeo packages, X-ray and Dask, and we have been employing a continuous delivery model, which is quasi-monthly for the last 2 years, to not only deliver whatever functions we are implementing as soon as possible, but also address in a monthly resolution the user feedback and bugs issued. This is the visualization component, which is GeoCAT examples and GeoCAT Viz. Maybe before going into the details, I would like to give a quick walkthrough it, because it is a plotting gallery actually. On the left-hand side, there are some tabs to navigate these galleries. So, in addition to the regular plotting galleries, there is also usage examples of the GeoCAT computational component in here, and this is what we recently added, and I will describe that effort in the upcoming slides. So, for now, we can have a quick look at the gallery. So, the GeoCAT examples right now has been housing slightly more than 150 plotting scripts in over 25 plotting groups or types. So some of them are kind of novel or were not trivially available in the Python visualization ecosystem that I just will show just in a few seconds in my slides. There are well-known plotting categories such as like contours and overlays and streamlines. Turning back to presentation. And yeah, that's the GeoCAT examples, and GeoCAT Viz is, as I mentioned before, introducing a higher level implementation on top of built-in matplotlib functions and cartopy projection functions. So in addition, it also introduces some contour and Taylor diagram classes and functionalities, and some other convenience functions as well, which is greatly useful for people who are transitioning from NCL world, because in the NCL, especially the plotting was very convenient. In just a few lines of code or few tens of lines of code, people were able to plot whatever they wanted in a publication quality. It was one of the strongest complaints from, at least from NCL user base, that they were kind of not happy with, lower level implementation with built-in matplotlib functions. So we introduced this GeoCAT Viz to make a higher level layer in between matplotlib and the user API, so they are now able to do whatever plotting they want in fewer lines of code, just like in NCL. In addition to that, you can also see some metrics to give some information about our user base amount right now. So on the right-hand side, I think I skipped one plot here. Okay, so this is, on the right-hand side, you can see Taylor diagrams and curly vectors. As far as now, and as of today, I don't think there is a trivially available and trivially available function, visualization function to put Taylor diagrams or especially curly vectors into a plot. So these are kind of novel things that GeoCAT Viz introduced, still with using matplotlib functions. And there are also some other like research kind of approaches from the GeoCAT team, like transitioning NCL's regular color maps to more colorblind friendly versions. So Wharf Python is still in limited but active development. Most of the functionality, most of the maintenance we are doing is supporting the user base requests. And one caveat with the Wharf Python is, actually it is the very first example of, or maybe one of the first examples of NCAR's Pivot to Python initiative, that it was written in Python, but at the time, like the year of 2017, it was not designed to be in the compatibility with Pangeo stack. Like it is not fully X-ray compatible, for example. So the GeoCAT team still has some agenda items to modernize this toolkit in the upcoming future. But it was a tool that reached out to many folks as the user base. So all of the tools, or almost all of the functionalities I mentioned so far, was heavily dedicated to the structured grids. There were some computational functions and visualizations in unstructured grid research from the GeoCAT, but most of them were in structured grids. So we have recently started to explore the unstructured grid field for data analysis and visualization purposes in scientific Python ecosystem. That's because, as you can see here, there is a big power coming from the unstructured grids as the resolution. But with that power, there are also some problems coming with that one. And first of all, even though there is the U-grid conventions in the unstructured field research, there is no widely used implementations to realize that U-grid convention or any other convention for the storage of unstructured grids in the Python ecosystem. And there are only a few analysis tools which are capable of working directly with unstructured grids. So most of the time, or most of the scientific workflow is still relying on regridding the unstructured grids first to structured or lat-long, then do whatever analysis they want. And finally, the global storm resolving resolutions, which are important for example, individual cloud analysis, are capable of generating lots and lots of data, which is also another raising a flag about the scalability. So it is also a challenge for unstructured mesh, not only analysis, but also visualization. We have been recently awarded by NSF EarthCube program on our project Raijin, and I put QR code to easily access to that project. It is a brand new project that we were awarded in the last year. As you can see here, it's a consensus between NCAR and Pennsylvania State University, and the GeoCAT team is in charge of the software development efforts for Project Raijin. So it has similar objectives to the original GeoCAT, but specifically on unstructured grids. So we want to develop extensible, scalable, and open source tools, and support fundamental analysis and visualization landscape for directly working on unstructured grids without needing to regret to structured. And open development is the same, as we would like to have a vibrant community around it. And we had defined some driving use cases for this unstructured grid research. So it is a dynamical core evaluation, atmospheric blocking frequency, and cyclonic storm analysis. I will speed up a little bit, so I'm in the last 5 minutes. So this is a notional component diagram that could show you how the realization of the project Raijin could in place. So we introduced a brand new UXArray package that extends XArray. That is for data recognition for unstructured grids. UXArray will natively support data models like MPAS and others, but it will also be extensible for people to put other data models for unstructured grid recognition. And UXArray is or will be able to run directly analysis operators on irregular meshes, but also it will provide regrading functions as well. So this is a tentative development roadmap which is open to discussion. So it is covering the entire 3 years, but again, it is open to discussions, and we are currently having discussions with the interested community members through our GitHub discussions topics. So there is already an active discussion about function prioritization. So regardless of this tentative roadmap, people are freely discussing whatever functions they would like to see in this toolkit in the initial stages or throughout the end of the 3 years. To implement UXArray package, we figured there was a very similar project which was awarded for DOE's SEEDS project. They were also doing almost the same set of functions for unstructured grids. So we have partnered with them. And again, UXArray is active as of today on this repository. We have released our first official release in June, and there is going to be an official release maybe this week or the next week with probably one analysis operators like integral calculation on global and regional mesh, and also we will have another August version with some other additional analysis operators. And we have currently been working on an internship project for visualization part of this. I would like to quickly touch this interactive visualization notebook as well, which we made use of a data shader stack for this. Let me quick walk you through this notebook. So this was on an Diamond data set, which has a various resolution set of 3.75 kilometers to 30 kilometers. For the local reproducibility purposes, we used the 30 kilometer resolution in this notebook, but at the same time, we analyzed the performance of data shader stack and our algorithms with 3.75 kilometers, which I would like to show you from here, the details. So it is around 42 million data points. And turning back, I would like to touch a few key items here. So the high performance, which is for the 3.75 kilometers or 42 million data points, just in a minute or two, you are able to process the data and see your plotting with the data shader stack. So that high performance is coming both from data shader stack as well as the fact that we are making use of connectivity information instead of using the costly Delaney triangulation as it should be required in Matplotlib stack. So I would highly recommend the interested folks to have a look at this one. And with the help of Data Shader stack, it is also interactively accessible. Turning back and speeding up in the last 1 minute. So these are our future directions. We would like to put more functions into the GeoCAT comp, especially and the UX array in the upcoming year. And we would like to put more notebook examples for visualization as well. And we would like to start some tutorials and demos, maybe in person and virtually in the upcoming year. And these are all of the communication information. Thank you very much.
Awesome. This time we'll go ahead and move on to questions. You can ask questions via the Track Questions Room 204 channel. So if you haven't added that channel onto your Slack, please go ahead and do so. So the first question here, how do you balance internal priorities and plans with those from external open source users?
That's a great question, and it is kind of a tough question to answer or to realize in practice as well. So actually it depends. For example, the UX array research or the unstructured grid research is also new to our team or the seeds project folks or many people in the Python ecosystem. So what we are doing in such a novel research field is we are keeping all of our discussions with the community members, but at the same time, we are clearly communicating that the team is new to that research as well. So we might be balancing between shooting first the low-hanging fruits for the developers' sake, and then, whenever we spin up and speed up, we can actually target the prioritized functions. So that's one thing. The other thing is, again, it depends on the toolkits. So if it is GeoCAT examples, which is almost all of the time, you know what to do for a visualization task under the GeoCAT examples. So we are almost 100% of the time prioritizing whatever request is coming from the community members. I hope that was an answer to the question.
Great, thanks. Next question. So does WRF Python have a simple WRF 2x array, like a 2 data set or something like that functionality?
Yeah, it's another good question, and it is what actually we would like to have, or we wish we had. Such a modernization item is in our agenda. At the same time, we know, and we were kind of in collaboration with another effort that was called XWRF, because of some stuff and other project management related topics, we couldn't do much contribution to that XWRF effort, but at the same time, we know this is kind of people's expectation to see WRF analysis in compatibility with X-array. So in the upcoming year, we would still put some effort to modernize as much as we can the WRF Python, or increase our collaboration with the XWRF or other similar efforts. So we will see.
Sounds good. Next question. So not necessarily a question, but Elliot, one of the asked about, so not a question that needs to be answered in talk, but as Matplotlib and CartoPy developers, we'd love to hear what your users find difficult using them for plotting, and asked to meet up at some point this week. So,
okay, yeah. The difficulty there is not with specific or individual Matplotlib functions. So there are many folks from like NCAR command language or maybe different backgrounds who are used to use fewer lines of codes for more work. So like they are used to use high-level implemented languages. So it is very much understandable. So it was a difficulty of satisfying that part of the user base. It was not specifically related to individual matplotlib functions or cartopy functions, but it was more of like providing people with, let's say, you group a number of matplotlib functions and put a higher level feature, just like a single line of code. So it was just like that.
Great. Another question. So, could you speak to sort of how you as a team decide like whether things belong within the GeoCAT suite of tools, or when you like submit things upstream, or sort of how you decide the scope of your project and what all belongs within that toolkit?
Yeah, that's another great question, and we almost always struggle with this type, because that's natural. So there are many efforts in the ecosystem, and there is overlaps. So that's understandable. I would like to give a good simple example. So there was a function, SKUT parameters, if folks in the audience know. We initially implemented this in our tool, then figured out it would be better placed in some other package that we can in detail, and we just upstream. Also, people from our user base says, or some of them say, it is good to have kind of such a landscape in the geoscientific ecosystem, and they want to see more functions in GeoCAT. So it is hard to make a decision like, hey, if we should contribute this upstream and get rid of it under the GeoCAT umbrella, or the existing user base who are already using GeoCAT comp or other GeoCAT components would like to keep that from a single package. So, but yeah, depending on the case, we are open to, you know, either upstream contribution or keeping that in GeoCAT umbrella.
Yeah. Do we have any other questions? No? If not, so you mentioned that a lot of your team, a lot of the organization was focused on NCL, and you kind of talked to this pivot to Python. What have been some of the biggest struggles in terms of getting the previous NCL users moving into the Python ecosystem, and how have you overcome some of that?
Yeah, that's another great question, and I think it is still, it might still be a challenge. People had their workflows and, you know, daily analysis codes and maybe thousands of lines of codes written in NCL. So it was not an easy decision for anybody else, I think, in the NCL user base. And they have just much experience in using NCL. So learning a different language, new language is a challenge for many people. They just want to keep their scientific analysis, like just, you know, with the same pace without needing to learn a new language. But at the same time, there are many folks who are much interested in transitioning into Python ecosystem. So the challenge was to hear but not be 100% able to help those people who were sad with the reducing number of, you know, NCL stats, and maybe when we put NCL into the maintenance mode. Again, it was not a happy decision for us, but since the team has limited number of people and we are agreeing with the pivot to Python initiative, so we had to make such a decision.
Awesome. Any other last minute questions? If not, again, thank you for such an awesome talk. Let's put our hands together for Orhan.
Yeah, thank you, everyone.